So for today, we're talking about rational functions, and I had the students graph for me y equals 1 over x minus 4, and then plus a 2. And most kids know that they start looking like this with asymptotes at 0 and 0. But then we have to move it. So, Joe, which way did it move?
To the right 4.
Correct. So the asymptote that was at 0 there moves right 4. And what other way did it move, Jay Kennan?
Up 2.
Up 2. So that's like this asymptote would be moved up to 2. Okay, good. And now...
The projector isn't.
Oh, you still can't see. All right, hold on a second here. Pausing for a second, technical difficulties. Okay, so, and from there, could you just kind of assume that the graph was going to do what it usually does and go, hold on just a second here. Now my Apple Pencil disconnected. Could you just assume it kind of go like that? Well, you could assume that, but you may want to check that. And on today's, we're going to be graphing weirder things where you won't know what's going to happen. So how do you get the points? I'm going to teach you where to put the asymptotes, but how do you get the points? XY chart. Your best friend in graphing. See, these things that I teach you over time are meant to come in handy at moments like this where you're like, oh yeah, I can always use the XY chart. We've done it like 7 times. Where you should be like, oh yeah, I'm going to stick a number in, see what I get. Okay, would everybody please put in 3, 4, and 5. And I want you to see what you get when you put 3, 4, and 5 into this function. And it'll verify some of the points that you should have had. I'll pause for a second. I'll give that a try. Okay, so here's me putting in 3. And I get 1 over -1, which is -1, plus 2, which is 1. 3 comma 1. Over 3 up 1. Whoa. Didn't expect that. Is that correct? I mean, is 3 comma 1 what you guys got? All right. So you see how I graphed it and it was like totally different than what I was expecting it to be? Yes.
Isn't the asymptote is 2, so like the line's like at 1, where you put it is like 3?
Okay, hold on. Over 3 up 1. Oh, okay, I just moved it up too high. Thank you. Good point. It'd be nice if I actually had graph paper. That'd be something that you would be provided on the test. So, okay, good. There we go. Sorry, it was actually okay. Now I'm going to try 4, and that one is one that should definitely have gotten weird. Why is it weird? You can't divide by 0, so then what's the answer? Can I just kind of like count that as 0 and then say the answer is 2? No. What's the answer? Undefined, and that makes an asymptote. When that happens, there's an asymptote. Oh, that's right. There's an asymptote at 4. We should have known when we stuck in 4 that you wouldn't get anything. All right, and then how about 5? Let's save some time. LeBlanc, what'd you get for 5? 3. All right, so 5 comma 3 over 5 up 3. Looks like about there. Yay, now I know I was generally right. Do you get if I wanted more points to connect more dots, you just find a few more numbers, stick in a few more numbers. Just keep doing that until you're confident you know where it is. All right. Well, I want to use this as a good example of how to find the vertical and the horizontal asymptotes. If I give you another function that doesn't even look the same at all, y equals x squared, hold on, over x minus 7. Would you agree that's totally different than this? Okay, but there's something that you can know about vertical and horizontal asymptotes from looking at this that'll help you. And that is that the vertical asymptotes you want to take notes on this. Vertical asymptotes are always x equals what makes the denominator 0. The vertical asymptotes are always x equals yx versus y, because then that would be a horizontal asymptote. The vertical asymptotes, I have a dumb way to remember this. I call them the vertical asymptotes. See, start with an X, like xylophone. The vertical asymptotes, because kids do get confused all the time. You're asked to list the vertical ones and people put y equals da-da-da. No, they're not y, they're x. The verticals are the x equals things, and whatever makes the denominator 0. So if you learn from that, you should be able to very quickly see a problem like this, for example. Sorry, technical difficulties. I don't know what's happening. Can't write on my screen, pausing again. All right, so if I give you an equation, y equals x over x plus 6 and x minus 8, I know this may bother you a little bit, but tell me what the vertical asymptotes are. Yes? Please say it with the letter in first.
X equals, wait, like x equals?
Yep.
X equals -6.
Why does that matter? Because it's a whole line. It's not just a point that's -6. It's a line at -6. And then x equals?
Positive.
Yep. So, look, if I graph this, at -6, there's an asymptote, and at +8, there's an asymptote. You can have two vertical asymptotes? Yep. All right. So, this is all about what are called rational functions. And I sometimes think it's worth taking a minute to talk about what rational means then. Rational numbers can be written as a fraction. That's, first of all, a definition that you're supposed to know for the ACT, is that rational numbers can be written as a fraction. So, well, can't everything be written as a fraction? Almost everything can be written as a fraction. Almost everything you've ever used. But there's a couple things that can't. Can you name one? Yes. You're right. Why can't you just say pi is like 3.14 and therefore it can be written as a fraction? Well, because that's rounding it. I know some of you might know that 22/7 is close to pi. Did anybody actually know that? It's really close to pi. So if you ever need a fraction for pi, it's that. But that's still just really close. It's not exact. Okay? Why can't I just get pi to be written as a fraction? Because it goes on forever and it never repeats. What's something else that goes on forever and never repeats? Anybody name another one? Square root of 2. And usually people that give that example just say that, and then I, for a while, thought that something was special about the square root of 2. No, it's the square root of 3 is also irrational, and the square root of 5 is also irrational. And why did I skip over the square root of 4? Because that's just 2, and that can be written as a fraction. So it's square roots of things that aren't perfect squares. Okay, so all of these things are irrational. Decimals that go on forever and never repeat. What if it repeated? Well, then you could write it as a fraction, like 0.7 repeating. What's that? You guys know the repeating ones? Well, you're going to find out right now. 7/9. 0.8 repeating. What's that? 8/9. And this one's going to hurt your head a little bit. 0.9 repeating. Let me lay some facts on you. 0.9 repeating is a repeating decimal. Repeating decimals have to be able to be rational numbers. And rational numbers can be written as a fraction. 0.9 repeating equals 1. it's not just really close to 1. It is 1. It's not just rounded to 1. It's 1. And if that doesn't hurt your head, it's only because you're not thinking about it hard enough. 0.9 repeating doesn't feel like it should equal 1. In fact, a lot of people will shy away from this one and say, oh, well, the limit as x approaches infinity, and I try to say it that way. But nope. It's not just getting close to 1. It's 1. And here's a couple little ways I can prove that to you. What's 1/3? 0.3 repeating, right? 0.333, etc. Okay, what's 2/3? 0.6 repeating. Would you agree if I wanted to take this as an equation that I can add anything I want to both sides? You know what I mean? If I want to add 2 to both sides, I can. Okay. I want to add 2/3 to both sides. So what's 1/3 plus 2/3?
1.
It's 3/3 or 1. Yep. And what's 0.3 repeating plus 0.6 repeating? Don't avoid it. It's 0.9 repeating. 0.9 repeating is 1. It's not just close to 1. It doesn't just round to 1. It's 1. Now this one is a little weaker in my opinion than what I said before, which was that all repeating decimals can be written as fractions because they're all rational. And if 0.9 repeating, therefore, is a repeating decimal, it must be able to be written as a fraction. And why would it all of a sudden just stop working? 7/9, 8/9, 9/9, which is 1. I have one more little proof. I actually like to sign off with this on my yearbooks sometime to remind you about something I taught you that you probably didn't know. And that goes like this. N equals 0.9 repeating. Would you agree I can multiply both sides by anything I want? I'm going to multiply by 10 on both sides. What's 10 times n? 10n. When you multiply a decimal by 10, you can move the decimal over and it'd be 9.9 repeating? Okay. Next. Would you agree, if I want to, I can subtract n from both sides? You can subtract a variable from both sides. And n is equal to 0.9 repeating, so I'm just going to choose to subtract that because they're the same. It says so right here. And what's 10n minus n? 9n. What's 9.9 repeating minus 0.9 repeating? 9n equals 1. That's a proof, boys and girls, unless there's something wrong. Did I break any math rules? I didn't. So it's true. Okay. I hope that bothers you a little bit, makes you think. So, rational functions can be written as a fraction. So these are fraction functions. Let's look at a few. All right. On this one, I already told you how to find the vertical. They come from the denominator. What's the vertical asymptote of this one? Short-term memory, anybody? X equals, no what? -1. X equals -1. Well, fine, server, you told us how to find the verticals, but you never told us how to find the horizontals. Well, I'm about to right now. All right. There's 3 cases you have to understand for horizontals. It's a little bit reminds me of the discriminant, where the discriminant can either be bigger than 0 or less than 0 or equal to 0. Okay, it's kind of like that. For the horizontal asymptotes, please, for your own sake, take notes. You'll remember 1/10 of what I say. I'm only going to give you 3 rules. That means you'll remember less than 1 out of 3 of them. Okay, so write them down. Horizontal asymptote rules. If it's bigger on the bottom, then the answer is y equals 0. What are you talking about with bigger on the bottom? This one, that's an example of a bigger on the bottom. Why? Because it's got the 5 down there? No, because the degree is bigger on the bottom. So this, I can confidently say, y equals that. It's a fraction function. It would have a line, a dotted line at y equals 0. That's the x-axis. So it would have an asymptote at the x-axis. All right. Next. What do you think is next? It's bigger on the bottom or it's... Yes?
Bigger on top.
Bigger on the top. And the rule for bigger on top is none. There is no asymptotes if it's bigger on top. I'll give you an example. Y equals x squared over x. Would you agree that just simplifies down to y equals x? Does that have any asymptotes? No. Bigger on the top, there's no asymptotes. There's one last scenario. Kind of like the discriminant. It was either bigger than 0, or it was less than 0, or it was equal to 0, okay? So this is either bigger on top, or it's bigger on the bottom, or it's what? Come on, say it if you know it.
Same.
Same. On both. If it's the same on both, then there's a rule that you take y equals a ratio. I want to give you an example one. Here's one that's the same on both. X plus 7 over x minus 3. Would you agree they're both degree 1 on the top? Would you agree they're the same on both then? So what's the rule for same on both? It's a ratio. The equation for the horizontal asymptote would be y equals, there's a 1 here, there's a 1 here, y equals 1 over 1. And yes, that simplifies to y equals 1. But I want to leave it as the ratio of those two numbers. Okay, verticals come from the denominator, but the horizontals have these 3 rules. Bigger on bottom, bigger on top, same on both. The only other thing you really need for today is that to find points on a graph, you can make an XY chart. You're almost done. You almost know everything you need to know. So let's do a couple and just like see if you really get this. Let's say I got y equals x over x squared plus 3. Is this bigger on the bottom, bigger on the top, or same on both? Say it if you know it.
Bigger bottom.
Bigger on the bottom. Well then, the horizontal asymptotes are the y ones. I like to say they're the horizontal asymptotes, you know, because they have a y in them, and you put that at the front of horizontal, and then you got horizontal. Why does that matter at all? Because it's often true that if I ask you for the horizontal or the vertical asymptotes, kids reverse them. And then I'll say, what's the vertical? And then they'll give y equals. Oh, that was the horizontal one. Horizontals are the y equals ones. Okay? And this is bigger on the bottom. So would you remember what I said about Bob's? 0. If you took notes, you'd have that. Y equals 0. Okay? Bob is a 0. But wait, there's one more thing we have to do to our rule for Bob's. This doesn't happen often. But do you get if I add 5 to the outside of this function right, like I just did? Not on the top of it, but if I put it on the outside, the whole function would move up 5? Wouldn't that take my horizontal asymptote that's going across like this and then move it up 5? Yes. So it's the rule for Bob's is a little more nuanced. It's y equals 0 plus outside. If there's anything on the outside of the fraction, like they decided to move it up 6, well then you got to take your y equals 0, it was going to be, and then move it up 6. So it's 0 plus whatever's on the outside. So I often say that Bob is an outsider. The bigger on the bottom kind. All depending on what's outside. And if there's nothing outside, then it's 0. Okay. So this one had a horizontal asymptote because it was bigger on the bottom, and it's y equals 0. Now I'm going to erase this 5 because it wasn't there before. So, how about the vertical asymptote? This one's weird. It seems like you could make the bottom 0, but you can't. Do you get you'd have to make x squared be negative 3? How can you make something squared be negative? With imaginary numbers, but not with real numbers. So then what's the asymptote? Well, if there isn't anything that makes the bottom 0, then there aren't any asymptotes. So this would be none. And what if I had to graph this thing? What's your best friend in graphing? XY chart. The XY chart is your best friend in graphing. Now, I would like you to try putting in 0, and don't think that that would crash the function because it doesn't. You get an answer. And then I'd like you to put in -1. And then I'd like you to put in 1. And I think there's something's going to freak you out a little bit here. I'll pause for a second. Let me give that a shot. Okay. When you stuck in 0, you should have got 0 over, well, 0 over anything. Unless it's 0 over 0, by the way. 0 over 0 doesn't exist. But 0 over some other number is 0. So 0, 0. And right there, holy crap, it goes through the asymptote. That's a new thing. You know, when you were little and you asked your mom and dad, how do babies get born? If you were young enough, they probably just said something like, oh, they grow in your mommy's stomach, or they are delivered by a stork. When you were young, we told you that you could never cross asymptotes. You can cross asymptotes. Now, it's rare, but it's complicated, and we'll be exploring that more in this unit. But anybody in here that hasn't had the word yet on Santa Claus? Okay, I won't say anything then. All right, so the asymptotes, you can cross, let me make sure I say this right. Vertical asymptotes, you can cross vertical asymptotes. We're still holding out on the horizontals, but, and you might be like, well, what's the point of an asymptote if you can't cross it? Well, you'll still get closer and closer to them and never touch them. But wait, you just said we can cross them. Yeah, but you don't touch it again. I know. It's like, all of a sudden, it gets so complicated. That's why we didn't try to explain this in the first case. But let's just get a few more points. When you put in -1, what do you get? -1 squared is 1, plus 3 is 4, -1/4. And Oscar, what did you get when you put in normal 1? 1/4. So 1 comma 1/4 is up here. -1, -1/4 is like down here. And I think, I'm not certain to be completely honest, but I'd need more points. But I think it's going to go like this and get closer and closer to the asymptote and never touch it again. All right, so one of those things that just has to eventually be learned by you is that in rare circumstances, you can cross the horizontal asymptote, but it'll still have that property where it'll kind of suck the function in, and in the long run, it gets closer and closer and closer to the asymptote and doesn't touch it again. Okay, so there's also something about the Easter Bunny I should probably tell you. All right, moving on. This is where you get your official definitions of vertical asymptotes and horizontal asymptotes. And holes. We haven't talked about holes yet. That's important. Let's go to number 2 right here. Find the yellow page, number 2. What do you think I'm about to say? Yes.
Factor you can, or you should.
If you can factor, you should. Yep. All right, so everybody get that thing factored. Dice of Destiny. Who should I call upon? Row 5, first person. Alyssa Stahl. What do you say?
Oh, x minus 2 x plus 3. Or, no, x minus 3 and x plus 2.
X minus 3 and x plus 2. You are correct. How about on the bottom there? Let's go with Owen Murtha. What is the bottom factor to?
X plus 3, x plus 3.
Close. X minus 3 and x plus 3. All right. Now, that right there, would you agree that it would cancel? But, do you agree that it's different than if it had never been there? Why? Because do you agree that if I stick a 3 in this function right here, if I put a 3 in it, a bad thing will happen? What will happen when I put a 3 in it? We'll have a 0 on the bottom. That can't exist. So when this cancels off, you can't act like it was never there. Positive 3 has still got an effect on this graph. What it does is it makes a hole in the graph. So imagine your graph was going along happily like this and this, but wait, at positive 3, which would be like out here, it just doesn't exist right there. Yeah, it's called a hole. Please tell me that in honors higher algebra, even during a pandemic, somebody told you that about holes. Raise your hand if you think you remember a hole being discussed. Okay, cool. Yay. So if the thing cancels, that creates a hole in the graph. So what you do is you graph all the rest of the function and you just look and go, well, wherever 3 is, x equals 3, that's going to create the hole, and you just put an empty spot wherever 3 would be. Okay? It is really common for kids to forget to graph that, though. Because, like they cross it off and then they forget it even existed. So if you ever do cross it off, better write hole for yourself to remind yourself, oh, it's not just gone. It made a hole, and I got to remember to put a hole in there at 3. Okay, now we've covered horizontal asymptotes, which have 3 rules. This is the part where I'm summarizing everything I taught you. Horizontal asymptotes. They're either bigger on bottom, bigger on top, or same on both. What's this one? Bigger on top, bigger on bottom, or same on both?
Same.
Same on both. Even after I cancel something, think about it, they'd still be the same on both. Okay, so what's the rule for Saabs? You might have to look it up. This is where it'd be smart if you had notes. Mr. K.
There is none? Wait, no.
No, you're thinking of bots.
It's 0.
There's 3 rules. One of them is that there is no asymptotes. One is that it's a bob, and Bob's an outsider and generally a 0. So that that's kind of rough on Bob there. He's a 0 and he's an outsider. But last but not least, we have the kind where they're the same on both, and that's a ratio. So what do you think the answer is? Ratio of the lead coefficients. Well, the lead here is a 1, and the lead here is a 1. So it's y equals 1 over 1. Y equals 1. So I know there's an asymptote, a horizontal asymptote at y equals 1. I know there's vertical asymptote at the other thing. We already know there's a hole here. A hole at 3. And at negative 3, it's whatever makes the bottom 0. Remember that? That's a vertical asymptote. I know, that's a lot. Whatever makes the bottom 0, that'll be a hole. sorry, not a hole, an asymptote. Holes are when there's something on the top and the bottom that cancel. And the horizontal asymptotes have three rules: bigger on bottom, bigger on top, and same on both. All right. So what else would you have to be able to do about this? Well, you would actually have to be able to graph it. Now this says using your graphing calculator. We won't have the graphing calculators in this test, so we just want you to be using an XY chart. Can you use the simpler function here? Yes. You can graph just that, but you got to remember there's a hole. The hole at 3. Okay. Let's sum it all up. Here is a typical question that you get asked. 3, x minus 3, x plus 4, all over x squared minus 16. Everybody write that one down. I would like to know, is there any vertical asymptotes? If so, what are they? Is there any horizontal asymptotes? If so, what are they? Is there any holes? If so, what are they? And then just to prove you haven't forgotten how to make charts, stick in 1 and tell me what you get for a point. And I know if you can do it with that, you can stick in any number and eventually find a whole bunch of points. Pausing for a second, let me give that a shot. So we've got, hold on 1 second, I'm just reiterating for the video. I canceled this to make a hole right there. Okay, good. And now you're telling me how to find the horizontal or the vertical? Miss B, you can do either one. The horizontal, okay. Is it a bigger on bottom, bigger on top, or same on both? There's that and that. And wait, this was still part of it before that canceled. Yes, it is the same on both. A lot of people think it's a bigger on the bottom, but no, you're right. It's the same on both. So what's the rule for that then? Very nice. Final answer. The ratio lead coefficients y equals
3.
Yep, 3 over 1, which is 3. Good job. All right. And Cal, can you tell me how to find the vertical?
Yeah, so I got vertical asymptote at x equals 4.
You are correct. What's the general rule for finding verticals?
Whatever makes the denominator 0,
Good. Why didn't you include the other thing that makes the bottom 0?
because that's the hole in the graph.
Very good. Holes take precedent. You can't be both. And if in the battle between the two, the hole wins. Okay. And I asked you to do one last thing, which is stick in a 1. Hennon, when you stuck in a 1, what did you get? Was it as simple as 2? Can anybody verify 2? Yay. I thought it was going to be a fraction, but the numbers were the same on the top and bottom. Sweet. Do you get if you just plug in a whole bunch of dots, you can graph anything? Just need to find more dots if you don't know where it is yet. We'd have graphed this asymptote, and we'd know graphing a whole bunch of dots. Oh, I can see where the lines are, and then put a hole in right there. Okay. So let's actually get you looking at the homework. Here's a typical question. Everybody work on this one. It's going to require you to figure out any holes. Don't worry about the domain of it. We'll worry about that later. Find the vertical asymptotes, horizontal asymptotes, if any exists, and then graph it. And it says a graphing utility. Nope. Just graph it with a few points on an XY chart, because you aren't going to have a calculator on this test. We'll make the numbers nice, but no calcs. It'd be too easy to just do everything with the calculator if you needed to figure out how far it moved over or whatever. I do stick to my, if you can factor it, you should, and there is a spot in here to factor. Okay, while you work on that, I'm going to hand back some tests. And I think that's going to be the end. We might finish this video by giving the answer to that, but if not, this could be the end of the video.